Okay, so for the next one, we're going to take a look at the group problem that we had. It's also related to some of the homework, and it's a good thing to be familiar with because it's one of the core things that we're actually dealing with our modern physics chapter. We have an energy diagram, and our energy diagram looks like this. Now, the way that I draw them, I like to set the ground state. Our ground state is this bottom shelf here. It's the lowest that our electron can actually go, so it's the closest to the nucleus it can get. I like to set that to be 0. However, if you look them up online, sometimes they'll have 0 at the very top and they'll have negative numbers. Since potential energies are all relative, you can always set your 0 point wherever you'd like to make things easier. So for me, I like to set my 0 point at the ground level and just have positive energies. That leads to my second one up here will be 1.9 electron volts, and up here I will have 3.4 electron volts. Now, I didn't mention it at the time, but where these numbers come from, these are actually only a handful of the orbits that are available inside the hydrogen atom. So, these are actually real-world values that we are dealing with, and we're going to see something come from these. For now, I'm going to deal with only these 3 energy levels and their transitions. Technically, there's other levels down beneath this guy. This is not actually the ground state. But for what we're doing, it's simple enough for us to make this approximation, and it'll be fine. So there are more energy levels, more colors associated with hydrogen than what we're actually going to see here. Now, the main things that I want to know is, I want to know what colors / wavelengths of light I can get out of this particular atom, this setup. So what I have you do is I have you imagine we have an electron, and it's up here on the top shelf. I like referring to these as shelves because it gives you the idea of you can set something on it, but you can't have something floating above it. It's got to be right there on that shelf. Okay? So I have it, and it can transition to several of these other places. I could keep my electron here on the top shelf, or I could put it here on the second shelf, or I could put it on the bottom of the shelf. It could be on any of these, but I can't have it just sitting there in the middle because, yeah, how often do you have things floating a little ways above shelves? They've got to be on the shelf itself. Shelf itself. I should really script these out better. All right. And so in general, what I'd like to know are the types of colors, the wavelengths of light that I can get off of this, and where they're going to fall in the electromagnetic spectrum. Now in the group problem itself, I have individual parts that it breaks down and kind of walks you through, so be certain to take a look at that particular document. I'm going to move kind of quickly through this so that we can see what's going on. The important things I need to know are, where am I going to get this light from, and what's going to determine its color? Well, my light can come from transitions, basically this electron moving around. Now, one of the ways that it can go from the top shelf all the way down to the bottom shelf. I'm going to call that transition 3 down to 1, where I'm now calling this 1, this 2, and this 3. That's an easy way for me to keep track of my energy levels. All right? So that's one transition. For that, it would lose 3.4 electron volts, and it's going to emit some light that has that 3.4 electron volts, because we have to conserve energy. That energy has to go somewhere. Okay, so one of the other ones that we could have is we could instead have our electron, it could fall from 3 down to 2. So 3 to 2, and then I can also have it, if it makes its way to 2, I can have it go from 2 down to 1. But at each point, when it moves from one shelf to another, it disappears instantly from that shelf and appears on the other. That's one of those weird things. Electrons like to be strange when they're bound to atoms. So it's never in between these. It's always either on one shelf or on another, which is kind of the weird thing, again, quantum mechanics. So when it goes from 3 to 2, it has to emit some light there, and when it goes from 2 down to 1, it has to emit light there. It can't just do all of them at once unless it skips over the second shelf altogether and just goes down to the first one. Okay? So going through this, I found that for my energies, I've got for energy of 3 down to 1, that was equal to 3.4 electron volts. For energy of 3 to 2, that came up to 1.5 electron volts. So as a reminder, from 3 down to 1, we went from 3.4 down to 0, so we lost 3.4 electron volts. In this case, from 3 to 2, we started at 3.4, we ended up at 1.9. So you do the difference of those two, and we've lost 1.5 electron volts. And then finally, we go from 1.9 down to 0, and we lose 1.9 electron volts. 2 to 1 equals 1.9 electron volts. Now, we're used to dealing with energies in terms of joules, so we're gonna go ahead and convert those. And we do that by taking, let's start with our 1.9. 1.9 electron volts times 1 electron volt equals 1.6 times 10 to the negative 19th joules. That's our conversion factor. You'll also notice that conversion factor happens to be elementary charge. It's the charge of an electron. Well, technically a proton because we always use the positive. But when I convert that to find the actual energy it has, did I write down my energy? Oh, well, technically 1.9 electron volts is an actual energy. But let's go ahead and find that. 1.9 times 1.6 times 10 raised to the negative 19th. We end up with 3.04 times 10 to the negative 19th joules. That's how much energy I have. Okay? But I want to find wavelength. I want to find the actual colors that I get out of this. So I've got my total energy. What equations do I have for energy? What can I do with this energy? Well, the main equation that we have is our energy equals Planck's constant times our frequency. So now I've got my energy. It's here. I'm going to plug that in. I know Planck's constant, H, that's 6.63 times 10 to the negative 34th joule seconds. All right? So I'll plug that in there. So I can find my frequency. In this case, F will be equal to our energy divided by Planck's constant. So I put that in. And I find that my frequency for this guy, which transition is this? This is 2 to 1 is the one that we're looking at right now. If I've done this correctly, my frequency should come up to 4.59 times 10 to the 14th hertz. That should be my frequency for 2 down to 1. And I apologize, I probably should have kept this in the color format that I was actually using. But take a look on how that's done. We convert our energy here into joules, which is something we're a little more used to using. Then we use Planck's constant with joules times seconds. However, we could have done the exact same thing and found the frequency by using the energy in electron volts and using the different version of Planck's constant with electron volt seconds, because then our units would work out. And we found that our frequency for our 2 to 1 transition was 4.59 times 10 to the 14th hertz. You'll notice times 10 to the 14th on a lot of the numbers that we deal with, mostly because I try and keep us around the visible range. And so that's going to be on the order of about several hundred nanometers or so. And so frequencies times 10 to the 14th are probably going to be common, but that's not the only things that we'll be dealing with. All right? And so keeping through with that, I'll let you do a lot of the hands-on math yourself, but 3 to 1, feel free to pause the video. But doing the exact same process that we did just a moment ago, except using 3.4 electron volts, which is the energy for our transition from 3 to 1, we end up with 8.21 times 10 to the 14th hertz. And then the last one, which was our transition from 3 to 2, equals 3.62 times 10 to the 14th hertz. Because I know that I want to find this for each of my types of light that I can emit, so I can find out exactly what all I can get. Okay? So, I've got my frequencies, but that's not what I'm looking for. I'm looking for wavelength. Okay, so we need one more equation. I know that my wave speed, which since we're dealing with light is going to be the speed of light, is equal to my frequency times my wavelength. Thus, I can find my wavelength by taking the speed of light divided by my frequency, which is 3 times 10 to the 8th meters per second, divided by, well, keeping with that first one that we were working with, 4.5. We use 4.59 times 10 to the 14th hertz. So I do that and I find that my wavelength, actually let me grab the green again, should really pay more attention to this, but my wavelength for my transition from 2 to 1, which corresponded to 1.9 electron volts worth of energy, is equal to 654 nanometers, is what I'm getting with the numbers that I have. All right? Now you'll do the exact same thing with the other frequencies, and you will find, I'll make a chart here. So 2 down to 1 gave me 654 nanometers, which is 6.5 times 10 to the negative 7th meters, which is what you'll actually get out of this. I should mark that. So this comes up to 6.54 times 10 to the negative 7th because it gives us the value in meters. We would then multiply that by 10 to the 9th to convert it to nanometers. I apologize. Hopefully that wasn't too confusing for you. I told you that you want to stay familiar with how to deal with nano and micro. 3 to 1. So that big energy drop from 3.4 electron volts, we end up with 366 nanometers. And then finally, wavelength for 3 to 2 comes up to 829 nanometers. And I ask you where in the spectrum it falls. This guy is going to be red. This one is going to be UV, ultraviolet, and this one is going to be infrared. And now I need to stop this because I have